Hi, my name is Manuel Kelly,
I'm Jimmy No.
and we are comparing the differences of implementing the RISC-V architecture on a PolarFire Splash Kit by Microsemi versus a Digilent Nexus4 DDR.
So this is the overview of our presentation. So we'll be talking about what is a RISC-V ISA, what is a PolarFire Splash Kit and a Nexus 4, what are their hardware differences, how do we implement RISC-V ISA on two FPGAs, and also future implementations. So what is a RISC-V architecture? Well, a RISC-V is an open standard set based on established reduced instruction set computer principles. It also provides additional ISA extensions to support privileged execution modes similar to x86, x64, and ARM architectures. RISC-V is also an open source specification for computers, processor architects, not a particular chip or implementation. So this is a PolarFire Splash Kit from Microsemi. So what is a PolarFire Splash Kit? A PolarFire Splash Kit is a field programmable gate array produced by Microsemi. The PolarFire has 300K configurable logic cells used for generating large systems via bit streams. This also has a 4 GB of onboard DDR4 memory. We also use this FPGA for our projects and will show how to build and generate a bitstream for it. We also will generate a RISC-V architecture on the PolarFire also. And so what is a Nexys4 DDR? Well, so Nexys4 is also a FPGA designed and created by Digilent. And the Nexus 4 provides roughly 64K logic cells for the user. This FPGA includes 128 megabytes of onboard memory. It also has DDR2 of memory. But due to COVID-19, we were unable to obtain the PolarFire, so we were basically using only Nexus 4 as our basis to implement RISC-V architecture. And when we were trying to implement them, we usually use Linux or Windows.
Okay, so the comparison between the PolarFire, Jimmy already went through a few things, but I wanted to line them up and show the big things. 300,000 logic cells versus 64,000. That's a big difference. You could build a much larger system on the PolarFire. 4 gigs of RAM versus 128 megs. Also a big difference. You can load much more, whether it be programs or software, you can load much more onto the PolarFire. The PolarFire uses the Libero IDE where the Nexus uses Vivado. The Libero is a little harder to use for like newer users, but it has a lot more functionality. The PolarFire has less peripherals as it's more specific for what your project is about, where the Nexus 4 is for learning for students, where it has VGA, it has input switches, it has audio out, it has a bunch of different things. The next difference is the PolarFire Splash Kit is almost 3 times as much as the Nexus. It's 2 to 3 times as much as the Nexus, where the PolarFire is $720 and it goes actually higher than that sometimes, where the Nexus is at max $320, but you can get it for much cheaper. So how do we implement the RISC-V architecture on the PolarFire? To start, we must search the IP catalog within Libero for the correct hardware cores and specifications. There are many subsystem cores such as UART, SPI, GPIO, and all of these are provided in the tutorial document. After we find all system cores, we move them into our smart design. Once all the components are in our smart design, we need to connect all of them. Once connected, our system will look like the figure to the side. After we have successfully connected our system, it is now time to synthesize. Synthesis will take some time, but after it is completed, we run the place and route process to configure our FPGA. After place and route is done, we need to verify timing of our system and import memory files that will be used during RAM initialization. Once all of this is complete, we can now generate a bit stream. If everything is successful, our design flow tab will look like the figure on the right. So how do we implement the RISC-V architecture on the Nexus 4? To start, we need a micro SD card, Linux VM, and to install Linux onto that VM. Next, we download the SI5 Freedom processor makefiles. To do this, we use the following git command. After we obtain the makefiles, we need to download the release files. These contain all the necessary files that would be written to the SD card. To do so, we run the following command. Next, we format the SD card and write the new files to it. Since we are using the Nexus 4, our SD card needs to be a file allocation table or FAT format. To format, we ran the following commands. The last thing to do is just to program the FPGA. Programming the FPGA is very simple. All we had to do was run the following command. Once programmed, we can then use PuTTY to view our results. And you can see in PuTTY on the top, it shows that it's loading the low risk architecture onto, or it loaded the low risk architecture onto the FPGA, and it's booting Linux kernel version 3.14.41, and then you can see it booting.
So for future implementations, since Manny talked about how the board can be used and how powerful it can be, so some future implementations we can probably do in the future is fault tolerance. So creating some software to combat any type of hindrance that may come in the system and protect them. Any type of RISC-V on a microcontroller. So doing some implementing some ISA to use microcontrollers and combining with MMI or VJ subsystems, and also we could also implement it in AI. So types of deep learning machine programs, powerful enough to compute all the data, process it, learn it, and accurately depict them or any types of information. And these are our references that we use, and that is the end of our presentation for our senior project.
Thank you.
Thank you.